Okay, so some of you have been having difficulty with the question from today, page 319 of the book, question 3. So what I'll do is I'll fire through the maths for you there. It is a bit difficult. It'll be a very hard question to come up, but if you follow log tables and things like that, when you see it, when I explain it, it'll probably make a lot more sense to you. So in the question, they tell us that the resistance is R. I'll move the tablet there now, so it's easier to write for me. Resistance is R. The number of turns is N, so N equals N. The length of the side, so the length is simply L. The velocity is V, and the magnetic flux is B. Magnetic flux density is B. Now, use Faraday's law to show that the EMF induced, so they show the EMF induced is given as the following. So they want us to prove that E equals NBLV. Okay, so that's the first part. Then it says get the current of the coil and the force of the coil. Okay, so prove this first. Okay, prove. So what we do first is go to the log tables, find the equation, and the equation is E equals minus, and then we can ignore that, N final minus initial divided by our time taken. Okay, so first things first is let's look at that. What is this? That is B times A. So B is B here, and what's our area? Length by length, L by L, so L squared. Okay, and our initial will obviously be 0 because it's coming into the magnetic field. Okay, so 0. All right, and then our time. Well, what do we say time is? Time, dad's silly triangle, distance divided by speed. You see? And what's our distance? Well, our distance is the side of the cube, the square coil, which they said is L. So our distance is L, and our speed is the velocity, which is V. So therefore, our EMF induced is going to be BL squared over L divided by V. Now, if you have a fraction, beneath a fraction, you have to pull that above the line, which will give us BL squared V over L, and that will get rid of that. And we have just proven then E equals magnetic flux density times L times V. Oh, I forgot about my N outside the bracket. Oops, okay, so the N is still there. I forgot to put in the N because the number of coils is actually N. So there you go. Okay, so go back over that again. So E is equal to minus N, final flux divided by initial. What is that? That is basically magnetic flux density times the area. They told us that the length of the coil, the square coil, let me just reread that. A square coil, so because it's a square, the area is length by width, which is L by L, which is L squared, so that's why it's BL squared. Time is distance divided by speed. The distance is the side going into the magnetic field, which is L, and the speed, which we were told in the question, was V, so it's L over V. And therefore, our equation then is N times BL squared L over V, a fraction below a fraction, pull that above the line, cancel them off, and there you go. Okay, so that's the first part, all right? So, part 1 is the current then. What is the current? Okay. So, go to your log tables. What do we have for current? Well, current is V divided by resistance. Okay. Now, this E isn't the energy. It's the induced EMF, which is the voltage. Okay. Don't forget that. That's a mistake. Don't worry, I make this mistake as well. Whenever I see a capital E, I think energy. But you got to remember for this, it's actually the induced EMF, which is a voltage. Okay. So, therefore, all right, what this is, our current is therefore our induced EMF from the first part. So that's going to be NBLV over R. Then that's it. That is your current. Okay? Because the induced EMF, and EMF is a voltage, a potential difference, a voltage. NBLV over R. That's part 2. Part 3 now is a little bit messy, or that's part 1 of the question. Part 2, they're asking for the force. Now this is an awkward one. This one took me a second to come up with, okay? All right? So what we can tell, all right, is we're going to say the force in the coil, all right? So force, and we're going to look at it in 1 second, okay? The work done equals the energy dissipated, okay? Now, if you look at power, that's on page, where's my log table is there now. So there's a few different things for power. Power equals VI and all that, and energy divided by time, okay? So power is energy, all right? So, okay. What do we think of work done? Work done is force times displacement, okay? Energy is equal to power over time, okay? Sorry, power is equal to energy divided by time. So energy is equal to power by time. So that's back in electricity, okay? I double check now my maths on that one. I'm probably getting it confused. It's probably power divided by time. Power equals energy divided by time. No, power is equal to energy divided by time, I think. It doesn't matter. It's equal to 1, okay? So our time is 1 second, okay? So it's basically our work done is equal to our energy converted, which is basically just going to simply be our power, okay? Energy converted. Okay? So it's power. Now, that will work into our advantage, the power, okay, in a second, okay, because we'll need to get that in, because the reason we're looking for power, the reason I want power is because I have current, and I need to pull that in. So that's obviously the value we're going to have to pull in here, okay, is the current there, okay. So energy converted, okay, which is electrical power, okay. Now, power is equal to I squared R, and we were told earlier the current is NB/LV over R, so that's going to be NB/LV over R to be squared times R. As you can see, this is getting very messy, okay? So that becomes N squared, B squared, L squared, V squared over R squared over R, and that R will cancel that. So our power is going to be N squared, B squared, L squared, V squared over R. Give me 2 seconds, I want to check. Yeah, okay, I'm on the right track. Okay, so I'm on the right track. That's almost what we need, okay? So that's on the left-hand side, okay? So the left-hand side is that, and the right-hand side. And on the left-hand side, we have this, okay? So F times S. S is, you could leave it as that, but we don't really have a distance in this question, okay? So let me see now. If you left it as that, you would have force is equal to N squared, B squared, L squared, V squared all over R times displacement. Yeah, that's usually what you would do. You would say R times or multiplied by the displacement, that's F. But I think in the back of the book, it says that it doesn't want that. It doesn't want S there at all. So we have to try to get rid of the S. Okay, so the answer to the back of the book was slightly different here. So, yeah, and also it says there in the question, derive an expression in terms of V. So in terms of V, okay, so in other words, if you can get rid of the other values. So S is distance. Okay, so what's another way of saying that? Again, displacement velocity by time. S, okay? So V by T. Okay? So therefore, work done can be rewritten as force times V times T. Now we said at the very start, the force in 1 second here. Okay, so the force in 1 second. So therefore, this equals 1. So therefore, work done equals force times velocity. Okay, so our work done here is equal to force times velocity. So what does that mean for our overall question then? All right, so let's pull it all back together. So now what are we going to have? We have force times velocity equals, what did I have here? Oh yeah, okay. N squared, B squared, L squared, V squared, all over R. And then this will divide off against that. F equals N squared, B squared, L squared, V, all over R. Okay, so how did I do that? Let's go back to the start. So what we said was, okay, so this was a hard one. This was a very hard one because you had to kind of tweak it a little bit. Work done is equal to energy converted. The energy we want to convert. So what we want basically is we want it in terms of V. So obviously we want it in terms of this thing here, okay? Because it's in terms of V. And then on the other side, work done is force times displacement. But again, we want it in terms of V. That's what the question said. So we got to try and convert to V if we can. Okay, so you have to remember force times displacement. What is displacement? Displacement is equal to velocity multiplied by time. That's why we're doing it in 1 second. The time is gone. Okay, all right. Energy converted is equal to power by time, and therefore time is 1 second. So therefore it's the power. Energy converted, okay, is the rate of power. Okay, so therefore what is power? So we look here at first for power, and we say, well, power in the log tables is I squared times R. And see, already now we've got our values in, you see? So we got our values in here by doing that. So power is I squared times R, which gives you this crazy long thing, N squared, B squared, L squared, V squared, the R's cancel over R. So that's the right-hand side sorted. Then on the left-hand side, we get it, work done is equal to force times velocity. Bring it back together, the V's will cancel, and then you're left with your final answer here. F equals N squared, B squared, L squared times V. Okay, hopefully that kind of clears it up a little bit. That is a very awkward question. Could I see that being an exam paper question? Not really. I wouldn't, because it's, I don't know, generally you wouldn't get a Magnus question like that. But the trick with it is, the reason I wouldn't think you'd get asked it is that the first bit you could get asked actually. You know, prove that if you did the equation with the values, you'd get that, okay? The current one, I could probably see as well, but the last one, not really, especially because if you left F times S, so if you left your work done as F times S and worked it out from there, you'd end up with the force equals N squared, B squared, L squared, V squared over R times the displacement. And technically you'd be correct, okay? But I think you'd be correct, except that the only problem is, of course, is that, that's why I don't think the last part would actually be an exam paper question, okay? Just because it's very awkward. They'd have to be more specific in saying that everything in the form of V, okay? That'd be the only thing I can really think of. So the first part with current and proving, I know that would happen, but the last part would never really happen in an exam. Like for example, I wouldn't have converted my displacement here into velocity by time. The only reason I did was that the answer in the back of the book was this. And so therefore the only way I could get that was if I converted my displacement into velocity by time. Okay, because it was 1 second, all right? So by doing that, I then got the value at the back of the book. But if you didn't do that, you'd probably be okay as well, because they never really specified that you couldn't have displacement. Okay, all right, so hopefully that answers that question for you guys and makes it a little bit easier. Okay.